So it is a pleasure to be here, to be back home in New York City. And what I'm going to talk to you about today are coupled oscillators and biofluids. I gave a talk recently at the Dynamical Systems meeting, and they're always talking about coupled oscillators. So I thought that I would be a little bit provocative and put that in my title, and then I realized I was a little frightened when I gave that talk, because I looked through the schedule on the PDF file, and there were like 150 mentions where coupled oscillators come up. So I'm going to tell you about how I interpret coupled oscillators. So first, here are some of my collaborators on the projects that I'll talk about. And my interpretation of hydrodynamically coupled oscillators. So let's think about swimming organisms, bacteria, sperm flagella, appendages of crawfish, and fish. Those kind of objects. I like to think about biofluid. I like to think about external biofluids, things moving where the fluid is external to the object. So rather than, let's say, blood flow in the heart. So my interpretation is that oscillators coupled to a fluid come in two flavors. Number one, there are oscillators that actually drive the rhythmic gates that we observe. So for instance, a lot of the coupled oscillator talks in a dynamical systems meeting are by neuroscientists who look at the periodic neural signal that comes through to perhaps, wow, yeah, I like it, to perhaps drive muscles, or the oscillators that I know some of you study here, molecular motors that somehow give rise to a periodic beating of a cilium, and they're somehow coordinated in space and time. Okay, so internal coupled oscillators giving rise to the rhythmic gates that allow things to move through a fluid. Or B, I also think about coupled oscillators as the appendages or the swimmers themselves. So let's see, here are some examples of low Reynolds number swimmers, like this eukaryotic sperm. This is a lamprey. So here, where one might consider these molecular motors, these dyneins that catch on to the neighboring microtubule, undergo conformational change and cause relative sliding. Here, that's what I'm considering. And here at the larger level, where the motion is driven by actin myosin, where it's the actual neural oscillators that are coming in to activate the muscles. So one broad question in biofluids is how is force generated due to the action of these oscillators. Here's also an example of my second interpretation of coupled oscillators in fluid, the swimmers or the objects themselves. So a lot of you know Bob Guy at UC Davis, and I think he was with Aaron Fogelson and took this video of some shrimp in a restaurant in Hong Kong. And here you see these nice swimmerettes that are paddling, and they are not paddling all in unison. You can sense that there's some metachronal wave going there. Here, these are bull sperm. This is from experiment by Woolley. And here you see these nice sperm are swimming. They're not really talking to each other, but at some point they come close together. Their waveform is in phase, and this picture is actually a picture of two sperm. So they are definitely somehow influencing each other, and how really are they coupled through the fluid is one question we could ask. And here you see the beautiful metachronal wave of beating cilia, and I forget what system this is. So again, the kind of questions that people broadly in biofluids are answering are of these two types. One, what is the mechanism that gives rise to this synchrony or metachrony of that nice wave of cilia that we saw, or the swimmerets of the crawfish, or the sperm cells? What mechanism is actually causing them to synchronize and coalesce? And also, which is a little bit easier question to approach computationally and mathematically, is given that arrangement, not worrying where it comes from, but given that arrangement, what are the functional implications hydrodynamically? And so what I'm going to do today is to it's Friday morning, it's icky weather out there. I'm not going to go into too many details of one particular system or any particular method, but I'm taking you through a journey of things that I've thought about and things that other people doing biofluids have. So all of the hydrodynamics, I'm assuming at the moment, is governed by the Navier-Stokes equations. Never mind that a lot of these objects exist not in a Newtonian fluid, but in viscoelastic or other very complicated systems. But for today, I'm going to only consider Newtonian. So here, I showed you the lamprey, I showed you the sperm cell. If we non-dimensionalize, we know that the Reynolds number is the all-important governing quantity, and so we could be going from tiny zero Reynolds number systems, which a lot of people here who are looking at cellular mechanics, that's the realm that y'all are in, all the way up to swimming fish, which could be 10,000. And so when we non-dimensionalize and take, for instance, the Reynolds number going to 0, we get the Stokes equation. And I like to think about the Stokes equations, and I like to think about what makes them so odd. So here, when we take the Reynolds number equals to 0, we have no time appearing explicitly any longer. At every moment, the system is in equilibrium. All of the forces balance. The beautiful thing that we all know is that we have fundamental solutions. So the Stokes equations are linear in U, in the fluid velocity. And so many numerical methods, many points of analysis make use of the fact that we do have a fundamental solution. So in all of our three, for instance, here, if we have a constant force or a fixed force applied at a fixed position x0 in space, then we can evaluate the fluid velocity anywhere given that force applied at x0, and here's the Stokes-Foote kernel. It is valid everywhere, except we have a 1/r singularity if we try to evaluate the velocity at the point at which you apply the force. Nevertheless, if you're applying a force along a surface, the 1/r singularity is integrable, and so it's all good. You could get the fluid velocity everywhere. The Stokes-Foote solution is we can write it down easily if our domain is free space, all of our three. We have fundamental solutions for above a planar wall, outside of a sphere. I really want one inside of a cylindrical tube, but I haven't found a good solution yet. But in any case, here we are, Stokes flow. You apply a fixed force at a fixed position, game over. You don't have to do any other work. But the fact is, And many of you are stuck in Stokes flow, aren't you? And so why do
That's
we?
the problem with Stokes flow. You're stuck.
You're stuck in there, right? We've got reversibility. You change time by minus time, which has a lot of implications in terms of stroke forms. Nothing could swim at Stokes flow in a Newtonian fluid if you just paddle and then paddle back. You will just move forward, and then when you put your appendage back, if you go through the same sequence of motions, you'll end up where you started. So Stokes flow is a little bizarre, but two things which makes Stokes flow more interesting and why we still actually work on it is what happens if the surface at which you're applying the forces is actually moving with the flow, and what if the forces are also evolving as the configuration evolves. So, the kind of problems that we solve, and I've discretized this just for the heck of it. Imagine that each of these points xk are points of the center line of this flagellum, and we have a collection or a summation of these forces. But now here, the points along the flagellum xk are moving with the fluid velocity that is the solution to this equation, and at the same time, these forces, let's say, if they're bending forces or elastic forces, they depend upon the configuration that is also moving in time. So this coupling with an elastic structure that's moving with the flow gives us, that's where the nonlinearity is hidden. And so that's what makes things much more interesting. Nevertheless, this equation is still linear in U, and we can still write down the solution for a fixed time like this in terms of the Stokes lit. And I told you I'm not talking about any numerical methods today, but for some of the systems that I'll show you, I've used regularized Stokes-Lit methodology, where instead of considering a Dirac delta function forcing term, one looks at a smoothed Dirac delta function, where if you choose it judiciously, you can write down an analytic regularized Stokes-Lit formulation. So let's come back now to some of these examples. And the eukaryotic axoneme is made up of the 9+2 structure, where you have these dyneins, molecular motors, which are laid out like a regular blueprint along this here, a fixed distance apart, and somehow these undergo an ATP-driven cycle, and the whole structure arises with, the whole structure gives rise to rhythmic shape deformations. So for the sperm flagellum, you have a sinusoidal type pattern that comes out, and if this was a cilium, which was anchored at its base, you would get a power and a recovery stroke. It is still very much not decided upon what are the individual actions governing each of these dyneins that give rise to that pattern. But one thing that I find very interesting, and here are some experiments from back in 1975. If you take this sperm, I think this is maybe a sea urchin sperm, I'm not sure, the same creature, and then you put it in fluids of different viscosities. And here are some snapshots by Charles Brokaw. Here's the largest viscosity. What you see is the gate modulation. So the waveform that arises from these interaction of these dyneins with the microtubules given this different external load is different. The waveform changes, the amplitude goes down, and the wave number goes up. So here's some simulations that I did with Bob Dylan many years ago, where we have where we were trying to model in this kind of very minimal system, where we modeled individual dynein motors that were undergoing an activation cycle that depended upon curvature, and here when we plopped it in a fluid with different viscosity, we saw similar changes.
Sorry, so just to understand, so the changes are a result of what? Of just change in viscosity for a fixed?
One parameter in a.
But what do you keep fixed?
Okay, what we have, so everything is a bunch of forces. So here, we had this structure that's made up of two microtubules here, and between them there are forces due to the activation of these dynein links. And so when we say, Mr. Dynein motor, you're active, we imagine that it's a spring that is contracting, that wants to have rest length 0.
But the program of contraction is independent of the viscosity, is that the assumption?
Yes, it's only geometric. It's only based on the local geometry.
Is that known, that there is no feedback?
No. So in this model,
okay.
In this model, the forces are all mechanical forces. They're dynamic mechanical forces that are being turned on and off based upon the local curvature of the structure.
Oh, I see. So
okay.
I see. Okay.
So
that's how they feedback.
That's it. Yes. I'm just not going into much detail here. But we took this construct where we had certain rules of activation, couple it with a fluid mechanics, and the only thing that's changed from here to here is one parameter.
And does that correspond to some sort of minimum energy expenditure or something like that?
Good question. I don't know. So let me show you this as well. So here is an example with two of these, the same simplified model, which I've not given you any details, where we take two cilium that are driven by, again, a curvature control model, where what I'm not depicting here are the individual dynein motors that are in between these two microtubules, but what you can see, I think, is that even though the two start in different phases of their power recovery stroke, after a very short time, they synchronize. And so what our claim was, this is back a long time ago, right? What our claim was is not that we have captured what is really happening within real cilia. We have a model of cilia that is driven by a curvature control, but we can observe synchrony only because of the external hydrodynamics. And I'll show you some other recent work in this. Okay. So now I'm going to take you in an opposite direction of Reynolds number. So let me just recap for a second so I could reorient myself. I told you I was thinking about hydrodynamically coupled oscillators in two ways. The internal mechanisms that drive the gate that we see, and B, the appendages or the swimmers themselves as coupled oscillators. I've given you a quick look at eukaryotic cilia and flagella, where the where the coupled oscillators are these dynein motors. I didn't give you any detail in the model, but in just showing you that, given if given a model that one chooses, you can see that they are coupled through the fluid. I gave you two examples of a model that I've given you two examples. One, the gate modulation in the sperm, where I've only changed the viscosity of the fluid to show you, yeah, these oscillators are coupled through the fluid. You get different emergent waveforms. And B, you get synchrony coupled through the fluid. Now I'm going to take you to some more recent work of coupled oscillators, where I'm thinking about the oscillators coupled through the fluid as neuronal oscillators. So this is part of a project that I have been involved with probably for the last 10 to 15 years, and this was started by Phil Holmes at Princeton, who many of you know, and Avis Cohen, a neuroscientist at University of Maryland, who has since retired. And one thing that neuroscientists are always looking towards is can we find an observed behavior that comes as a function of neural signaling, where that behavior is easily measured. And so swimming of a simple undulatory organism like the lamprey is a good example. One could measure the emergent waveform and swimming performance. And on top of that, the lamprey that I'm showing you here is a nice model organism in the sense that it is the most basal vertebrate. So it is got a simple neural wiring diagram down its spinal cord. And on top of that, and this was due to Avis Cohen and others decades ago, the preparation is fairly simple, not for us theoreticians, but for the biologists. They have their way of taking out the spinal cord of a lamprey, putting it in a dish, putting it in the right amount of chemicals, and putting electrodes in, and they could measure the neural wave that is still coming down. Okay, so there's been a lot of work on what's called fictive swimming, because that baby, he's not swimming, he's just a spinal cord in a dish, but nevertheless, one could measure the propagation of neural signals down the spinal cord. And so the whole system that, if you think about a swimming fish or a swimming C. elegans, what have you, we could think about it as the coupling of all of these different features, where we have some neuronal network, some central pattern generator that's giving, let's say, signals to the motor neurons that's driving the muscles. The muscles then have to interact with the passive structure of the body. That's coupled with an external fluid mechanics. But then at the same time, the swimmer has a sensory system. There's some proprioception that could perhaps help to stabilize the swimmer. The neural signal is feeding back perhaps from the body curvature. So all of this is one big coupled system, and maybe 15 years ago or so, when Phil and Avis started this project, they recognized that there was a lot of experimental work and theory where people kept themselves confined to one of these boxes. And so the hope was to put the whole thing together and see how the swimming emerges from the coupling of all of these systems. And I'll show you a little bit of what we're doing here. So the CPG, this neural network, should be modeled, let's say, by Hodgkin-Huxley type equations, but we're going to start in a very simple way where we look at coupled oscillators. So you recognize here, this looks like the Kuramoto oscillator equation. with some forcing terms. So let me just show you a little bit. So the lamprey itself is driven by two sets of muscles, left and right side, that fire in antiphase. So here is some readings. Here we have right 7, right 19, left 7, left 19. And here, if you put an electrode in the spinal cord in the dish, you see the periodic firing of the right segment 7. You wait a little while, and you see the same firing in the 19th segment of the lamprey. So you see that there's a traveling wave of firing happening here. If you look at left 7 and left 19, you see, here's right 7, on. They're firing in antiphase. So when this signal that's going to the motor neuron for all these segments to contract the muscle, we don't really need to resolve those fine spikes. The information that we're getting from these recordings is this on and off. We're getting the frequency or the period of firing, and we're also getting the phase differences. So the first attempt, a simple attempt, rather than taking into account any of the details of the neurons, is to model this CPG as a phase oscillator model. Because what I'm telling you, that what we're interested in the information here is not the amplitude of the spikes. We have an on-off signal. We want to capture its period, and we want to capture the phase shifts between each of these. And so here, each muscle segment, whether it's on and off, we're going to model as a phase oscillator. And then how is that going to be somehow fed in as a signal to the contracting muscle? So here is what we want to capture. If we then assign each segment an oscillator, we could come up with an on-off signal like this. So here we assign an angle theta. We take sine of that angle. We put in a cutoff that would determine the duty cycle, and then we get an on-off signal. If you look here at the simple phase oscillator system, so here's a natural frequency. If we tune this so that we have a constant phase shift of phi here, and if we have, what am I showing you here? These are coupling along one of the sides, left and right. But we also have coupling across. Across, we would want them to be in opposite phase. That's why we have the pi here. And here, along the body, we're tuning this with a phase shift. If we have nothing here, and we start out all of our oscillators with that given phase shift, and where the oscillators across on the opposing side, if they're started off in antiphase, then these clocks, these oscillators, would all move at a frequency omega. Well, what we're doing instead here is in this coupled oscillator system, what we're going to have some sensory feedback, in that we're either going to speed up or slow down our clocks based upon probing the emerging curvature at that segment. So I'm not giving you much details of this coupled system, but what I'm telling you is we want to have a swimming system where we have a very simple CPG model, but that CPG model is going to get information from the evolving body curvature. Now, I should say that here I have the sensory feedback coming from the actual curvature, but recent experiments in my collaborator Eric Teitel's lab is showing that these, the CPG responds more significantly to the rate of change of body curvature. Okay, but that would be another set of models here. So here's the mechanical model that is coupled to those coupled oscillators that I showed you in this way. So here is a swimmer, a very crude swimmer that is made up of a center line. Think about it as some structural spinal cord, if you will. And it is made up of two parallel segments. And these segments support different types of forces. Number one, there are passive elastic forces or Hookean type springs holding the whole structure together. Number two, on each one of these, we have a passive collagen type spring, but we also have activated muscles. And that whether or not that muscle is activated depends upon certain muscle models, for sure, but whether it's activated or not depends upon that signal from the neural system, which somehow is coming from those values of theta, the oscillators. And now we're going to put all of this together and put it in a fluid, and certainly this is not a Stokes fluid, but here we can see a beautiful swimmer. And again, I'm not giving you any details, but what I'm showing you is the lovely vortex wake that is being shed. I will tell you what the shadow is in a minute, but what is input into these calculations is not the emergent body form or the swimming. What is input here are all the material properties of those networks of springs to mimic the body structure that I showed you. The external fluid velocity is input, the CPG is input, and the maximal muscle contraction strength. What emerges from the calculation is the swimming. I should say that here we're using immersed boundary method, IBAMR, which is an adaptive mesh refinement where we refine the mesh near the swimmer and in regions of high vorticity. The shadow here is the control swimmer without any sensory feedback, and the red and blue swimmer that you see has a particular form of sensory feedback. So let me just give you an example of the kind of things that we can play with here. So one of the forms of sensory feedback that we explored is the following, is that we're imagining that curvature to one side at a particular muscle segment is going to either excite or inhibit the oscillators on that side, and it's going to do the exact opposite on the other side. Okay? So if we do that, here's what we get. And when I say excite, there's going to be a coefficient in front of this term, in the feedback term that we call the gain. And if it excites that side, it's a positive, and it inhibits that side, it's negative. I don't remember which is which. So here are two examples where the gray is the control. There's no feedback at all, meaning that neural signal, when there's no feedback, that neural signal is coming in to the musculature no matter what. It is not changing. It is the same signal. Even if there's some external perturbation, the swimmer is not sensing its body curvature, and it is going to be fixed throughout the simulation. In the other two, so this is, I don't remember which is positive or negative, One thing that you should see as well, you know, everything looks pretty much the same. The ones with positive feedback, negative feedback, the body shape doesn't look that much different. They do swim more slowly, yes?
So is the simulation in 2 dimensions?
Yes, it is. So this is,
Is there anything that changes? You have 3 dimensions?
well, we won't know until we do that,
Okay.
right? But that certainly is a next step. There is a lot of detail in this model that I have to say, my editorial comment here is, I find it remarkable that this thing actually swims the way it does in 2D. We have so much detail in the muscle models. We have calcium driving each muscle. We've got the CPG and so forth, and we plop it in, and this guy swims. What we have done is compared these models to other 3D models without, not the internal guts of it, but we've compared these models with both robotic models, real swimmers, with pressure gauges and vortex shedding and so on, and it's remarkable how much the 2D model actually picks up in the overall fluid mechanics. But this really should be done in 3D with better body structure, for sure. So like I said, there's not much information here, but you know what? This is a computational model, and unlike in the lab, we have a lot of, we've kept track of a lot of things, and let me show you what I mean. So for instance, here's my gain coefficient going from negative to positive, and just look at one of these lines. We could compute the cost of transport. So yeah, the swimmer everything looked basically the same, but we could compute, this is like miles per gallon. How much work is done for this swimmer to get from here to there? That's what, or how much energy is expended. So we see that there's, here's the control with gain 0, we see that the cost of transport goes down by an awful lot, by 30%. When we have this feedback. And so then we want to look under the hood a little bit more to see what is giving us this savings in this cost of transport. So I'm going to focus on this picture for a while and focus on this middle here. Now, this is for a particular segment, let's just say, this particular segment, let's say the 100th muscle segment on the body. And red is one side, blue is the other, right? They're firing in antiphase. And so this is the activation signal. So the red one is off. The red one is on, the blue is off. They're both, there's some quiet phase between both of them. Then the blue goes on, meaning that muscle is contracting, and then it stops contracting, they're both off, then the red starts, and so on. Here is negative gain, here is positive gain. So just look here for a second. This is just the on-off signal. This is based on those thetas. You can see that when this is the same time period, the frequency is the same. Here we have on, so we're not on twice. The duty cycle's different. The amount of time during this interval that the blue one is on is less here and more here. Okay. This is the activation signal. The activation signal feeds into some calcium model, which feeds into a force, a contractile force. That's what you're looking at here. So if you look here, so this is just on-off. This is the neural signal, whether it's on or off. That neural signal, whether it's on or off on that muscle segment, here's the force that we compute. So look what happens here. When the blue signal is off, here, when the red signal is on, the force starts building up, and then it decays, but it is still on here. It is, the red force is still positive, while the other side is now contracting. So this region here is co-contraction. You have both sides trying to contract. That's not very efficient. So what we see in the negative gain case, you have a large period of time where you have both the red and the blue contracting. You have a lot of co-contraction. But if we go down to the positive gain case, there's almost no co-contraction. So it turns out that even those simulations that I showed you, where it basically looks the same, this particular form of sensory feedback with, on-off on either side, or inhibit and excite, here gives rise to this. Now, is this what's really happening in the animal? I don't know. But it's our luxury as theoreticians to try all these things out and to help guide the experiments. The next step really in this project is going to be, we know that we have to change the phase model to a neural model of some type.
Does the negative feedback case go faster? Does it swim faster, even if it's less efficient?
I don't think so.
No, it's just a crappier swimmer
Yeah,
together.
yeah. But you can read our paper, and I wish I remembered the answer to that, which is just fairly recent. But let me talk about some exciting new work that I'm involved with. Where I'm part of a project of 17 investigators that went out to NSF NeuroNext program just last week on studying the neuromechanics of 3 different types of undulatory swimmers, and I'm part of the fault tolerance research group. So let me show you what that is. So I'll show you those here. These are from Jen Morgan's lab at NBL up at Woods Hole, who is the PI of this project. These are 3 lamprey, and she goes in and ablates the spinal cord of these guys.
How big is this? How big is the? That's the size of the lamprey?
Yeah. Yeah, what else would it be?
I don't know how big they are.
So there's the control swimmer, and you see that one is, let's see.
Oh, man.
Here. The control swimmer is the happy fast guy. The one that's 1 week post-injury, you see things are not so good, and the one that 3 weeks post-injury is a little bit better.
Does the spinal column heal in these creatures?
It does, yeah. So in fact, Charlie, I know you said that, here's the control and 11-week post-injury. So there's regeneration here. So there's a whole bunch of questions and what we think modeling could do. Now, the guy that recovers, what do you think is what's happening with the neuromechanics, with the neural network? Are certain connections coming back? Are some not coming back at all, but others getting stronger? These are the kind of things that they don't know. Now I know that there's incredible new experimental methods and technology that can really go in and measure lots of these things. But what we're hoping to do from the modeling is to how do we say it? In silico ablation of these neural connections, and then measure the fault tolerance of the system can it still swim? I will tell you, it is, again, what my point before, we've done this where we've just zeroed out muscle activity. It's remarkable that this 2-year-old swimmer still actually swims. So what we want to do is also cut out things, measure the swimming behavior, but then we want to somehow model recovery and see how we can change strengths and topology of the connection and see how that gives rise to different swimmers, and hopefully use that to suggest some experiments on where to look. So that's what we're doing right now. I want to just show you, let's see, I didn't get to part B. I'll show you some cool movies. Swimmers or appendages as oscillators. I talked about internal oscillators, that's good. And so what I want to do is to give a shout out to some other people's research. And so here again these are the swimmerettes from the restaurant in Hong Kong. And you know, one thing that completely makes me crazy every time I hear Bob Guy and Tim Lewis talk about the project, they pronounce this as crayfish. It's crawfish. Those are crawfish, not crayfish. So,
Must be from Philadelphia.
huh?
It sticks in your craw.
Okay. So they did some very nice work where they didn't look to see what happens with metachrony, but they modeled the power and recovery stroke of these swimmerettes, where so the swimmerettes don't just paddle back and forth.
Are they really called swimmerettes? That's each of these paddles is
They
called a
are.
swimmerette.
I did not make that one up.
Swimmerettes.
So the way they modeled this was that during the recovery stroke, the paddles were permeable to fluid. It's a nice simple model, and they specified the stroke in each of these. Here, everything is in phase. Here, there's a phase difference from front to back, and there's a phase difference from back to front. Rather than looking at these guys swimming, they pinned it down and looked at the pumping mechanisms. And so you see, after it settles into a nice state, they put a bunch of fluid markers. There they are. And here, the guy would be swimming this way, so the most efficient swimmer would be the one that pumps enough fluid in the back. And they saw that the arrangement of this particular phase shift in the metachronal wave gave rise to the most efficient pumping. But
Could you, when you said something about permeability, that was to mimic three-dimensional effects of flow going around?
I'm not sure if it was three-dimensional effects. I think the swimmerettes, when they beat in one direction, then they beat back. Like there's some change in morphology.
Oh, I see.
They like
I see.
fold in, they go like this and then they come.
Yeah,
fold
so there's a
together.
change in
Oh,
morphology.
It's like you turn the oar.
Yeah.
Okay.
So let's see. I'm just going to show you some other. Now, so that's an example where one showed that what the effects of metachrony were, not how it happened, right? Let's go back to Sir G.I. Taylor. How could I not go back to Sir G.I. Taylor? The first paper in biofluids, basically, external biofluids, where he studied the swimming of an infinite sheet. And then he also, in that 51 paper, he looked at at two swimming sheets, one next to each other, and showed that the minimal energy configuration, someone talked about a minimal energy configuration, actually occurred when the two sheets beat in phase. Their energy was expended in his calculations. That was first order in amplitude. But the swimmers only swam up to second order in amplitude, and he didn't carry out the energy calculation to higher order. And what happens, in fact, is that the two sheets adjust their swimming velocity so that one swims faster than the other if there's a phase offset and they actually synchronize. So I put this picture up here for you, Mike. Remember that?
I do.
Okay, so here's an example where G.I. Taylor stated that if the sheets are in phase, that is the minimal energy configuration. But how that happened, well, in the swimming sheet case, we saw, and we did this in viscoelastic fluid, that the difference in swimming velocity brought that together. Show you just, well, what really happens in 3D, or what really happens, nothing is clean like this, but we saw that that in Woolley's experiments of sperm, they coalesce. Now, this Taylor's swimming sheets, or Mike's swimming sheets, could never do this because the fluid in between is incompressible, and so the two sheets could not come together, squeeze out all of that fluid. However, finite swimmers can squeeze together 2D or 3D. So I just showed you a quick simulation here where these are actually Kirchhoff rods in a 3D fluid, and you see that nice coalescing. No surprises here for those pusher and puller enthusiasts in the audience. These are our pushers. We know what the flow field looks like, fluid coming in from either side and fluid being pushed in that direction. So we would expect sperm to coalesce. And let's see, just finally, I'll stop here. Here is a lovely simulation by Suk Lim and Charlie Peskin and others, where if you think about these flagella as coupled oscillators in a fluid, where each one of these is semi-rigid rotating helices attached to a cell body, if they all, let me show you Berg's movie. Here you have this nice flagellar bundling, which comes from the coupled oscillation of these semi-flexible filaments. And this is a good place to stop. I have way more examples of other cool things that other groups did if you're at all interested. But thanks for listening.
Nice picture.
Oh, yeah, and that's what I should have ended with
Yeah.
this one. Another beautiful example of now where you could learn things by using minimal models. And I wanted to, yes. So I shouted out to some of my friends in biofluids.
Yeah, this was a real score for computational fluid mechanics.
Right, because here, I believe that here are the experiments of Bacillus subtilis, here are Kayla's computations, and when fluid mechanics is ignored, you do not replicate this circling in one direction, circling in the other. Is that?
Yeah, they had published a paper first where they had misinterpreted their results, actually, about why they were observing these patterns, and
Right.
Kayla didn't believe them, so she.
So here's my Flatiron shout out.
Yeah.
Thanks.
Great, thanks.